Hi, welcome to Celtomic. We are officially back again. Today, we'll be covering on covalent bonds. Earlier, we did a video that shows how compounds can be formed using ionic bonds. You can click on the top right hand corner to view that video. Now, we will learn how compounds can be formed using covalent bonds. So, covalent bonds are formed by the sharing of electrons to gain a full octet structure. This takes place generally in non-matters. We'll now see how these two atoms form a covalent bond. So the atoms has a valence shell of 7 electrons as the atoms form a covalent bond when they share an electron. So this sharing of electron can be showed using a dot and cross diagram. So now we see two circles and each circle represents an atom. So the sharing of electrons are depicted when they are drawn in the area where the two circles intersect. So we can use a dot to represent the electron from one atom and a cross to represent the electron from another atom. This pair of electrons here represents a single bond. 2 pairs represent a double bond and 3 pairs represents a triple bond. So let's move on to the dot and cross diagram so that I can illustrate to you better. So in a dot and cross diagram, there are a few things that we need to take note of. First, we need to draw only the valence shell unless the question says otherwise. Second, we need to include a legend. Third, we need to check that each atom has a full valence shell. And fourth, we need to check that each atom has the correct number of electrons. Points 3 and 4 will be shown again later when I finish drawing the dot and cross diagram. So for example, we are doing the dot and cross diagram of methane, also known as CH4, this one. So our legend states that the cross will be used to represent the electrons of the carbon and the dot will be used to represent the electrons of the hydrogen. So for us to draw the dot and cross diagram of methane or a covalent bond in general, we usually look at the first atom. So in methane or CH4, the first element that comes out is C, also known as carbon. And generally, we can use C to be our central atom. So I'm going to draw a circle. And this is our carbon. Next, I'll draw the 4 hydrogens around the carbon atom. 1, 2, 3, and 4. And I'm going to label them as hydrogen, 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 and hydrogen. Before we continue, we need to know the number of valence electrons on carbon and on hydrogen. From the periodic table, we can see that carbon has 4 electrons on its outer shell. For hydrogen, we know it has 1 electron on its outer shell. So later, when we draw in the cross and the dots into the diagram, we need to take note of 4 and 1. So first, let's put in the electrons of hydrogen. So hydrogen only has 1 electron, so all we need to do is just put 1 dot in the intersect. And these dots here represent the electrons that H is willing to share. Now let's draw the electrons of carbon. Carbon has 4 electrons, so it can share 1 electron to each hydrogen atom. 1 here, 1 here, 1 here, and the last one here. So now we need to check points 3 and points 4. So we need to see whether each atom has a full valence shell, and we need to see whether each atom has the correct number of electrons. Let's start with the first one. We need to check whether each atom has a full valence shell. So a full valence shell for carbon would mean that it needs 8 electrons in its outer shell. A full valence shell for hydrogen means that it needs 2 electrons on its outer shell. So let's count for hydrogen. This hydrogen has 1, 2 electrons, so this is correct. So this has 2 as well, this has 2, and this has 2. So our hydrogen is correct. Now we look at carbon. Carbon needs 8 electrons from its outer shell. It has 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons in the outer shell of carbon as well. So this is correct. So one thing to note, when you see me count earlier, I count the pair of electrons that are shared. Even the dots that do not belong to carbon, I count them as well. This is because these electrons are now being shared with the carbon, so we can include it in our calculation for the full valence electron. Now we need to check whether each atom has the correct number of electrons. So we need to check whether each hydrogen has 1 dot and whether the carbon atom has 4 crosses. 1 dot, 1 dot, 1 dot, 1 dot. Hydrogen is right. 1, 2, 3, 4 crosses. So the carbon is also correct. So that is how you draw a dot and cross diagram for a simple molecular structure. A covalent bond generally has two structures, a simple molecular structure and a giant molecular structure. For this video, we will cover the simple molecular structure. So the properties of a simple molecular structure are that it has a low melting and boiling point, it is a bad conductor of electricity, and it cannot dissolve in water. The reason why a simple molecular structure is a bad conductor of electricity is because the electrons of the molecule are being used either for sharing, or it can be found in the valence shell of the molecule. There are no free electrons left in the molecule that allows it to conduct electricity. We'll now move on to see why it has a low melting point and it cannot dissolve in water. Low melting and boiling point. In order for us to explain why simple molecular structures have a low melting and boiling point, we first need to understand what van der Waals forces are. Van der Waals forces are actually intermolecular forces of attraction between molecules. What this means is that the forces of attraction between two neighboring molecules. So this is one molecule here, this is another molecule, and this is another molecule. The van der Waals forces, or the forces of attraction between these molecules, are very weak, such that very little energy, or heat in this case, is needed to overcome these van der Waals forces of attraction. And since there is low energy needed or low heat needed, this means that it can either melt or boil at a very low temperature. Hence, it has a low melting and boiling point. Lastly, we'll look at the ability of simple molecular structures to dissolve water. I have grouped the compounds into two sections, non-polar and polar. Polar molecules such as nitrogen, also known as N2, CO2, we also have examples like O2. All these are non-polar molecules and they are not able to dissolve in water. On the other hand, polar molecules such as HCl, hydrochloric, ammonia, and H3, all these molecules here on the polar section are able to dissolve water. This is because they form hydrogen bonds with the water molecules, and that allows them to dissolve in water. So one way to depict hydrogen bonds is like this. First, let me draw a water molecule. So this is the water molecule, and now I will draw in the hydrogen bond between it and the hydrochloric acid. It's because of this hydrogen bond here, it allows the HCl to be dissolved in water. And hence, there are some molecules, which are the polar molecules, that are able to dissolve in water, and there are the non-polar molecules that are not able to dissolve in water. So that's all we have for today. I hope that you will continue to support us. We will continue to put up videos for the next few weeks. And now we have also started an Instagram page. So the Instagram page is Celtomic. Please go and follow us and also subscribe to us. And please like this video if you think that it has helped you. So that's all we have for today. Stay curious and we'll see you in the next video. Bye!